Perfect. All right. So thank you for having me. It's a pleasure to be here. I'm going to talk about, again, discovering dimensionless groups from using machine learning methods to discover dimensionless groups. And this is work I've done in the last 2 years with Nathan Kutz, Stephen Brunton, and Jared Callahan. So, there's this general theme of dimensionless groups that has mostly been ignored in the past couple of decades in data-driven modeling. And I think it's kind of a rare topic to teach in engineering and science. It's very common in fluid dynamics, for example, and it's found everywhere in physics, but not really as common as I think it should be, at least. So I usually like to motivate that by looking at physical systems that have very different significant dimensionless groups. For example, if you compare a flying hummingbird to a swimming microorganism, they both swim in a fluid, and the fluid follows a Navier-Stokes equation, and that Navier-Stokes equation can be found in from the smallest fluidic systems to the largest ones. And it's the same equation that describes the same dynamics, but the major difference between these two organisms experiencing their environment is just one number, the Reynolds number. And for larger Reynolds number, the organism will experience a very turbulent flow, a much more inertial flow, so to speak, while for smaller organisms, you have a much more viscous flow. So this organism has to kind of struggle in order to sort of deform its surrounding. And just one number, which is a combination of input parameters, can tell you a lot about the regime in which these organisms are experiencing their environment and the regime of the fluid around them. And in fluid dynamics, you can see a lot of these numbers, but in physics in general as well, which is, for example, Reynolds number is density times the velocity times the density times the characteristic length divided by some viscosity of the fluid. The Struhal number is related, for example, to here, if you have oscillating flows, the frequency of oscillations times the length, which is meters divided by the velocity. So you can see these numbers are defined in such a way that when you combine these input parameters, you get something that's dimensionless. And here, when I talk about dimensionless, if you're not familiar with the concept, it's really unitless. It has no units. For example, Reynolds number is a combination of these input parameters. And if you put them together, mass divided by length cubed times length divided by time times length divided by mass divided by length divided by time, this combination, you'll get something that has no units. So why would you want to use these units if this is not motivation enough? One reason for using the units is that you can simplify nonlinear dynamical systems or nonlinear models in general. And that's, again, something that you find in fluid dynamics. Because it's a nonlinear system, you often need to approximate the equation, not solve the equation. So that makes solving it numerically or analytically much easier. And you do so by non-dimensionalizing the equation and identifying which terms are small. So you just get rid of terms where your coefficient or your dimensionless coefficients are either too small, or if they're too large, then everything else cancels. So it can be done without modeling, as we will see now with the Buckingham pi theorem. And it's a form of lossless dimensionality reduction. In data-driven methods, we often talk about dimensionality reduction, where we take very high dimensional system and we try to compress it because it generalizes better. So you have less features, so less overfitting. And in this case, you can actually reduce your dimension without losing any information from the data. So you're not trying to minimize some kind of variance, but it's just the symmetry is inherent in the physical dimensions themselves, and you can do that dimensionality reduction. So when you take this high dimensional parameter space of velocity, viscosity, length, density, frequency, etc. in this case, and you project it on lower dimensional space, you also get a very interpretable space. Here, for example, in terms of Reynolds and Struhal, where for low Reynolds you have a laminar flow, for large Reynolds you have a turbulence flow. So this is like there's a transition, a qualitative transition in the solution, going in the Reynolds dimension, and going in the Struhal dimension, we also go to oscillating flows, for example. So it's also an interpretable parametric space where we can look at different regimes in different parts of this coordinate system. And of course, this what I just mentioned is a form of bifurcation and scaling analysis. And these are all physically interpretable change of variables. So when we go from a dimensional to a dimensionless space, we're looking at something that is much more interpretable than just going to, for example, if you just do SVD or PCA, where you go to a lower dimensional. So you have dominant modes. Dominant modes often have some interpretation to them, but they're not necessarily physically interpretable. Here, we're combining input parameters. And for example, in the case of Reynolds number, there's viscous forces compared to inertial forces. And so this is much more physically interpretable than just dominant modes. Of course, when it's possible. Sometimes it's not possible, and that's the best we can do. And the other motivation is that these numbers are often not known in many systems, like in non-Newtonian fluids, in geological systems, even in fluid dynamics, where you have very high Reynolds number with diffusion. We don't know how to define the Reynolds number in many cases. In complex systems in general, these numbers are not known. So the problem we would like to solve is, given data of these systems where we don't know dimensionless groups, can we find them from the data by sort of collapsing this data on lower dimensional space and taking advantage of what we already know about dimensionless groups. So before I proceed, does this make sense to most of you? Because I know some people are not familiar with dimensionless groups, and I want to make sure that everybody is on the same page. Okay, I'm assuming that everybody's on the same page then. So how do we usually find dimensionless numbers? Let's say we'll take a simple problem where we have a pendulum. And in the case of a pendulum, the inputs are the gravitational constant, the length of the string, the mass of m of whatever is used in the pendulum, and the time also, which has dimensions of seconds. These are input parameters, and the output is the angle alpha, which has no dimension. And in this case, what we can do is we can take that pendulum, we can just do the free body diagram, and we model it, and we get this differential equation for the pendulum. And we can non-dimensionalize it in order to get a dimensionless differential equation. And the coefficient in that dimensionless differential equation is actually a dimensionless group that in this case tells you, for example, about the period of oscillations for small angles. And in of course, what I mentioned earlier in the Navier-Stokes equation, that would be your Reynolds number or your Struhal number. But what you can also do is go immediately from the parameters and variables and deduce what the dimensionless groups are using the Buckingham Pi theorem. But using the Buckingham Pi theorem, which is a procedure of combining these parameters, gives you a non-unique set of dimensionless groups. In the case of a pendulum, it is actually unique. But in other cases, like in fluid dynamics, you can have infinitely many dimensionless groups, and there's no, and it really depends on expertise to know which dimensionless groups are relevant and which aren't. And also, there are many ways to non-dimensionalize different differential equations. So what we want to do is take data and add it to the data to the Buckingham Pi theorem in order to inform the theorem as to the best set of dimensionless groups that are physically meaningful in that specific case. So again, the Buckingham pi theorem takes in inputs P and output Q and maps it through a function F. So usually F is a solution to a differential equation. And what the theorem says is that we can actually take this mapping Q equals F of P and go to a dimensionless coordinate system, pi Q equals psi of pi P, where we don't know what the function psi is, but we know that this mapping does exist. And we also know what the dimensions of the inputs and the outputs should be. Now, we can we can say what the Buckingham pi theorem is algebraically by saying that d phi equals 0. This is like this simple equation illustrates what the Buckingham pi theorem is, and I'll tell you what d and phi are. So if we have dimensional inputs, p tilde, so these are p tilde are the inputs and outputs concatenated together, and pi are the dimensionless outputs. Or dimensionless outputs and inputs. So we want to map dimensionless dimensional inputs and outputs to dimensionless inputs and outputs. And that mapping has this specific form where we don't know what the powers phi ij are. For example, in the case of a Reynolds number, your dimensional inputs and outputs are rho, v, d, and mu, and your powers are 1, 1, 1, minus 1. So these are in the phi matrix. And of course, if you have multiple dimensionless inputs and outputs, you get a matrix phi. So then the matrix D contains the omegas of your dimensional inputs and outputs, p tilde. For example, in the case of a force, the dimension of force is mass length divided by time squared, and the omega of F is 1, 1, minus 2. So that goes into one of the rows of D. So let's say now you have force, density, velocity, etc. Every one of those rows will tell you what the dimension of each one of these input and output parameters are. So given these two definitions, we know that the matrix phi, which is what we're looking for, the powers of your dimensional numbers, lives in the null space of D. So that's d phi equals 0. And when you solve this equation for different rows of phi, you'll get basically what your dimensionless outputs, dimensionless parameters are, these pi that we're looking for. And sometimes this equation, finding the null space of D, gives you a unique solution, but most of the times it gives you infinitely many solutions. So the question is, in the case where phi is not unique or doesn't have a specific value, where we have infinitely many options, how can we choose the one that's the most relevant in our problem? So we want to leverage a given data to do that. And now just a quick note that the probabilistic sort of corollary of the Buckingham pi theorem is that when we're doing dimensionality reduction, we're going from mapping P to Q to mapping pi P to pi Q, while preserving the error. We're not losing any information, which is something that I mentioned earlier. And the biggest hypothesis that we're making here to develop the methods that I'm going to explain in a bit is that the optimal set of dimensionless groups or dimensionless bases pi star that takes us from the dimensional coordinate system to the dimensionless coordinate system minimizes this loss. So what you can see inside the parentheses is we're trying to basically find a fitting function that maps pi p to pi q, which the Buckingham pi theorem tells us it exists, and it tells us what the dimension of pi p and pi q are. And while doing so, we're also trying to find the best set of dimensionless groups that gives us that mapping. So here there are two minimization problems. And in this case, finding these pi groups is in a way finding these hidden variables that give us the best mapping from inputs to outputs. So now the question is, how do we constrain the set of all possible pi groups, and how do we define the function psi? So we developed three methods that sort of build on this hypothesis. And that's constraint optimization, which uses this d phi equals 0 as a hard constraint and finds a non-parametric function c. The second method is the Buckynet, which uses a neural network with a constrained layer that again uses d phi as a soft constraint. And then the sparse identification method that gives us not only dimensionless groups, but also a parametric differential equation with dimensionless coefficients. Okay, so again, before I proceed, any questions? All right.
Maybe a quick question, Josette.
Yes.
It's super exciting stuff. And just on the when you were mentioning that the probabilistic analog of the like the dimensional reduction, I mean, you had some epsilon bound. So how does that work, right? Because I mean, you cannot be approximate in terms of the dimensions, right? So is it just to account for like errors, or so that was like 2 slides ahead or whatnot?
Yes, that's a good point. So this is sort of not proven really, like there's no hard proof for it, but the logic behind that is that usually when you're in the deterministic case, you're doing your dimensionality reduction and you're not losing any information. So if there's no error epsilon, then, and you're not actually fitting a function, but the function is actually a solution of the differential equation, you can do that deterministically and there is no problem about it. Here what we're trying to say is, so this epsilon might be multiplied by a constant in this case, but what we're saying is that we're not losing any information. So the variance of the data of the noise isn't increasing when we're doing that dimensionality reduction. But we might need to have a proof for that, maybe more rigorously, but there's no proof. But the general idea is that there's it's a lossless dimensionality reduction.
Okay, thanks so much.
Does that answer your question?
Yeah, thanks so much.
Okay. All right. That's a good question. So let's start with the first method. The first method takes in our input data matrix P, logs the input data matrix, and multiplies it by some function phi p that we're trying to find that has these are the powers of the dimensional parameters, and then applies an exponential to that. And then we apply the psi function to this dimensionless group now. It's a dimensionless data to get the dimensionless output spike q. In this case, we're assuming that we can easily non-dimensionalize the output. For example, in the case of a fluid, you just divide the output velocity by the free stream velocity or the average velocity. We're not non-dimensionalizing the pi q as well. So we're just trying to find the best dimensionless inputs. And we're assuming that we have the dimensionless outputs. And we add these regularization terms to our loss function, and we apply this hard constraint on d times phi. Here, the subscript p means that we're defining d and phi just for the inputs, not for inputs and outputs. And you can see the parallel between this sort of exponential of log of p times phi with how we defined earlier the relationship between p tilde and pi, right? So this phi, these are the powers, and when we log them, we can bring out phi from the power out of the log. So we have, of course, a regularization in order to make sure we're not overfitting the data, and we have a hard constraint. So we're using, in this case, psi as a non-parametric Gaussian radial basis function. And we're also using a kernel ridge regression to optimize this constraint optimization problem. So to show you one benchmark, one example is the laminar boundary layer. Let's say we have a laminar boundary layer, we have a plate, and we have a flow above that plate, and it's a laminar flow. So all the velocity streams are parallel. in U, and you have this nice distribution U of xy that's not a function of time.
Sorry, can I ask a question on previous slide? Sorry, I'm afraid that if I don't ask it, I cannot understand anymore. So here, what I didn't get well is that, so we don't know this pi of q, right? So how can we use it to predict?
We don't know
pi
q. So right, so we're assuming that we know pi q in this case, which as I just mentioned, this method assumes, which is not the case with the other methods, later methods, is we're assuming that pi actually, so let's say q is the velocity, because that's what we're trying to predict in the next slide. Then pi q is just the velocity divided by the free stream velocity. So maybe an example here will be easier to understand. If you have u of xy as the quantity of interest we're trying to predict, then u of xy divided by u infinity, which is the free stream velocity, is my pi q.
Thank you.
Makes sense? Yeah. So that's one of the sort of shortcomings or limitations of the methods here, is that some of them we have to assume that we know what the dimensionless outputs are, and we're just trying to non-dimensionalize the inputs. There are ways we're also now trying to, we're developing methods that kind of non-dimensionalize both inputs and outputs efficiently. The disadvantage with these methods that might be that in some cases, when you have many parameters, non-dimensionalizing both outputs and inputs is not as efficient. And the way we formulated them are just much easier for just non-dimensionalizing inputs. So in the case of a laminar boundary layer, we have we can derive a PDE for the stream function, and it's a steady state stream function, not a function of time, but it's a function of y and x. And you can see these third order derivative in y and second order derivative in x and y. We know from the fluid dynamics theory that we can actually transform this very nasty PDE into simpler ODE, still nonlinear, by just changing variables. So if we define eta as the new variable and say that eta is y times square root u free stream velocity divided by kinetic viscosity times x, the distance of the from the plate, then we can find an equation for this new function f of eta, defined like this as a function of the stream function, and we get this simplified ODE that we can solve much more easily with these boundary conditions. Now, of course, the question here is, can we, in this case, just take in as inputs our x, y, and nu, and try to figure out eta without having to derive it analytically? Here, it took years to derive the theory by Prendel and Blasius, but in our case, we just want to use data to infer that the optimal scaling. And using constraint optimization, as defined earlier, we find that we can get pi p, which is our input, to be very close to eta. And here there's also one thing that we're assuming, that y has a power of 1. We have to scale y to have a power of 1 so that everything else falls into place. In many cases here, we get some pi p to the power some number. So 0.1, 0.3, all of these are actually dimensionless, but they're sort of a power of eta. What we get is a power of eta. And if you look at the data now, plotting eta as a function of the output, the dimensionless output, u divided by u infinity, we can show that the data actually falls on this scaling. So we collapse the data on a lower dimensional space. Okay, so does that make sense for this method? Now I'm going to go to the next method. Okay. By the way, how much more time do I have? I know there's 40 minutes rather than an hour, so
I guess we usually keep it to like under an hour, so like probably 30 more minutes. But if you want to leave some time for questions, that would be good too.
Okay. All right. So yeah, I'm going to try to not take too long so that we can discuss the methods rather in 10 to 15 minutes. Okay. So the second method is BuckyNet, which is a neural network, and you can see that we define the loss in the same way, where we're trying to minimize this phi p matrix. And the only difference is that instead of using a hard constraint to minimize d phi, this hard constraint d phi equals 0, now it's a soft constraint. So we add it to the loss, and we're trying to minimize it in an L2 sense. So this is dimensionless loss. And just for illustration, I'm going to use the pendulum problem to illustrate how the method works. So let's say here we have M, L, G, and T as inputs, and the output is the angle alpha. So what we take these input parameters P, so that's your matrix capital P. We apply a logarithm function to that, and then we multiply it by the function phi. That could be in a neural network that's just the first layer, these connections taking you from the first layer to the second layer. And here we know that we're looking for just one dimensionless group, and we apply an exponential to that output. So that's the exponential, and here it's an activation function. So the reason I'm framing it in terms of a neural network is because you know, there are a lot of neural networks out there that use input-output mappings, and they usually don't account for the dimensions of the inputs. So this is easy to sort of add to your deep learning algorithm by just defining an exponential activation function and by just logging the inputs. You also have to make sure that your inputs are positive so that you don't get so that the logarithm function is well defined. And then once you exponentiate, now you have your dimensionless input that we're looking for. And we're trying to fit the function psi also as a neural network that maps the dimensionless input to alpha. Here, alpha is just dimensionless by default because it's the angle in radians, so it has no dimension. Again, we're minimizing this dimensionless loss just approximately, and we're using this hyperparameter lambda, which can be tuned to make the dimensionless loss either a harder loss or a softer loss, kind of making it more important or less important. Again, this is a part of the machine learning workflow where we also have to optimize over lambda. But in this case, we actually don't have to optimize over lambda because what we get is we get an approximate phi, and then based on that approximation, we can infer the actual dimensionless group. So for example, in this case, we get phi to be minus 0.0025, 1, and something close to -1, something close to -2. And this is really just discovering that GT squared is GT squared over L. And it makes sense because in the case where you have a small angle, the solution is given by alpha 0 times cosine square root of this number, GT squared over L. But in the case of large angle, this is not the solution. And yet the network manages anyway to find this proper dimensionless group. Now, this is a simple example because you can actually do that by hand. You don't need this driven method. But it's also interesting because it works without including the dimensionless loss. Sorry.
Joseph, may I ask a quick thing?
Yes.
So how important is lambda to get to that, right?
Yes, it's in this case, it's not important at all. In the case of the pendulum, and it really depends on other problems. But in general, it's you'll see in later problems, it could be sensitive to lambda, but in my experience, it doesn't play as big a role as in other machine learning algorithms.
Thanks.
Can I also ask a question?
Yeah.
If we train this model like a few times, do we get the same results, or like, in phrase differently, how do you know like how large is the uncertainty?
Yes. So again, in the case of a pendulum, you have no uncertainty. You'll get numbers that are close to these integers. We're not imposing integer values, but you'll get something very close every time you train. But in other cases, it is sensitive, and that's a good question, which I'll tell you in a bit. So let's say we're trying to discover two-dimensional groups instead of one. So this is an example that illustrates that. Let's say we have this is a classical problem in nonlinear dynamics, that rotate of a bead on a rotating hoop. We have a bead sliding on a hoop, and there's this angle between the bead and the vertical x, and has radius r with a drag coefficient b, that drag on the bead for sliding on the hoop, and an angular velocity omega, and has a gravity g. Now we know we can derive the differential equation for that. It's a second order differential equation. It's very nonlinear because it has sines and cosines of x. And we can non-dimensionalize this equation to get this epsilon and gamma defined as r omega squared over g for gamma, and epsilon is m squared gr over b squared. Now again, the question here is, if we just have x of t, so x as a function of time, we have solutions of x of t, but we don't know the differential equation, can we infer these dimensionless groups? Now, what's interesting about these dimensionless groups is that for epsilon very small, then you get a first order equation, and you don't have an inertial term, and you don't have oscillations. So that's sort of epsilon controls your inertia. And gamma controls bifurcation. It's a bifurcation parameter. So if gamma is greater than 1, then we just have, and then we get 2 extra fixed points. If gamma is less than 1, then you have 2 fixed points that are at x equals 0 and x equals pi over 2. And at x equals 0, it's an unstable fixed point. X equals pi over 2, it's a stable fixed point. Because if you start at the bottom and then you start rotating, then the bead will automatically slide to go up. It's like the opposite of an inverted pendulum. But if gamma is greater than 1, you get a pitchfork bifurcation. And there are 2 extra fixed points at x star equals plus or minus r cosine of gamma. So you have these fixed points are actually a function of gamma. And if we discover that gamma is a significant dimensionless group, we also discover its bifurcation parameter, and plotting the solution in terms of it will give us a lot of course, physical insight into the problem. So how do we, again, can we apply the, for example, the Buckynet problem, Buckynet algorithm to discover gamma and epsilon? So again, the same illustration, we have input parameters, we log those, and we multiply by phi, and then we apply an exponential activation function to get these 2 dimensionless groups. And we map these dimensionless inputs to the output, which in this case is the angle, but instead of using time as an input, here we use a different trick, which is we take these time-dependent output, and we get the time mode. So now we're just trying to find the time mode of the oscillations of the output, so that it reduces the dimension of our problem. And in this case, with the Buckynet algorithm, we find this solution. And this solution is the network doesn't always converge to the solution. So this is one of the instances. And the network sometimes converges to a suboptimal solution, but if you take, for example, if you're optimizing over lambda, you do a hyperparameter optimization. So for different lambdas, you'll get a different loss and a different set of these dimensionless groups. And then you take the loss that is the lowest. So you're just optimizing over lambda. And another hyperparameter here is the architecture of phi or psi. So if you have a larger network, you'll tend to overfit, and that will not generalize well, and you will not actually get the proper dimensionless groups. So there are hyperparameters, of course, that you're optimizing over, and you will not always get exactly these dimensionless groups.
Joseph, I have a question
Yes.
regarding that slide.
Yes.
How do you decide that there are 3 time modes? Is this the 2 unstable ones and the other one, or no? This is just what the SVD gave you.
This is just what the SVD gave me. So actually the modes are also the number of modes are also a hyperparameter, and having less modes, like 1 mode is not enough, and having 10 modes is so what we discovered is at least 3 to 4 modes will give you these dimensionless groups, and it's really a matter of also optimizing over these. It's kind of straightforward to see that when you get to very high modes, you're overfitting. But we also did some, which I didn't include here, some analysis on for each given mode, how many times we actually converge to the expected solution. So there's one thing that sort of I didn't mention, or I kind of mentioned at the beginning. So we know that there are infinitely many ways to non-dimensionalize this data, right? And if we know the differential equation, there is a natural way to do it, and that's because we know a lot about the problem, and gamma and epsilon are the most natural. But sometimes the algorithm tells us, gives us other dimensionless groups, and these might also be significant in the problem. So there is no, when we say the correct solution, we're not actually saying that there is a true solution. It's what analytical methods tell us is the most appropriate solution. So other solutions might be also important to look at, but in our case, we just drop them because we're looking for something that we already know. And analyzing what we get that is not what we expect is something we haven't really looked deep enough into, but that would be also an interesting thing to look at.
Thank you.
So
I agree. I was actually interested in like the statistics of where it goes wrong and stuff, but I think this is fascinating regardless. So I think there's also another question here.
Okay, yeah, other question.
I was going to ask, like, are you adding, so you're doing this on data, like, are you adding uncertainty, or are these like exact solutions, and like how much uncertainty?
Good question. Yes, we're not adding uncertainty. So we, in all these machine learning algorithms, what we're usually getting is the expectation. So we're not looking at the variance of the solution or the distribution of the solution, because we're just looking.
I bet the input, like you have a dynamical system, like a model for like the pendulum. Are the input samples that you're putting in, like, are these exact solutions to these like dynamical equations?
Yes.
Or okay, so there's no like uncertainty at all, or like kind of a noise on the inputs?
No. So what there is we're sampling from distribution of M of these input parameters,
Okay.
and each one of these samples. So you can say that we're actually sampling from a probability distribution of these input parameters, but that's not really uncertainty, because like once we get these samples, the simulation itself, there is no uncertainty in the solution itself. But yeah, I don't know if that's really considered uncertainty. And the way we're thinking about it is that we're trying to get solutions in parameter space that fill parameter space as much as possible. But and in our case, we're doing it using a uniform distribution. It would be interesting to see if like we have different distributions over the parameter space, if we get different results. That's that could be. I don't know if you were thinking in that direction, but that could be something to look at. But yeah, adding noise to the data, for example, might affect the solution. But we did look into that, and there is robustness to noise up to a certain extent, and at some point it becomes we start getting dimensionless groups that don't make a lot of sense. That very that they're still. Some of them are still integer or simple rationals, but they're a little too complicated, I would say. And so again, to talk a little more about these suboptimal solutions that in a way can be thought of as a problem with the method or maybe as insight into the solution. So what happens sometimes is that we get in a lot of these suboptimal solutions, in this specific case, is that we get a linear combination. So one of the dimensionless outputs is like epsilon is some gamma plus, it's a linear combination of gamma and this dimensionless time scale that I didn't talk about. So if we try to non-dimensionalize time, tau, we get a tau that is usually mg over b. But because we're not including time explicitly in our problem, what it does, it includes omega instead of t. So we have mg over omega b rather than mg over tb. And then you can see that, for example, this is one possible solution. We get gamma times tau to the power 2/3 in this case, and here to the power 0.88. So there's something, it's found something that seems to be like a simple rational, but not clear what and how significant it is. So maybe just plotting these the solution as a function of these dimensionless groups will give us more insight as to why these suboptimal solutions are happening. But yeah, there's more work to be done in terms of analyzing solutions that are not exactly what we expect. And that becomes significant in problems where we don't actually know what the real or the most accepted dimensionless groups are. Okay, so we can get back to that when people have more questions. So the last method is builds on the idea that physically meaningful equations are dimensionally homogeneous, which means that you can only add apples to apples, or you can only add things that have the same dimensions to each other. And usually what you do is in any differential equation is you divide, all the apples by one of the apples. And this is a little pushing the analogy here, but then you have to deal only with numbers that have no units. And then if one of these numbers is very small, then you can ignore it and assume that your equation is still balanced and solve it accordingly. We saw this in the Navier-Stokes equation, for example, for low Reynolds number, then you have a viscous dominated flow, so you can get rid of the inertial term. And for very high Reynolds number, you can have, for example, you can get rid of the viscous term. So given that idea, the question is, can we get a differential equation that that is dimensionless? And the dimensionless groups that we're looking for are actually coefficients in that differential equation. They're the quantity of interest, which is here pi q, for example, is the output, and pi p will appear as coefficients in this differential equation. So to do that, we define this d pi q dt, which is, if we non-dimensionalize time, it's 1 over the time scale t times d pi q d tau, equals some function of pi p and pi q. These are the dimensionless inputs and outputs. And what we're assuming here is that f is separable. So this dimensionless outputs are pi p, dimensionless inputs are these coefficients. And the output can be written as a dictionary of terms. Here I'm just showing polynomial, but that could be sines or cosines of pi p, like what we get in a bead on a rotating hoop. And it's multiplied by this matrix C that we're looking for. These are the coefficients. If you're familiar with Cindy here, I I included acronym without defining it. This is sparse identification of nonlinear dynamics. If you're not familiar with it, I can talk about that in more detail at the end. But the idea here is to actually infer a differential equation from the data. So we built this library of functions that's a function of pi q and t, and the coefficients now are these pi p. And what we're trying to optimize for in this formulation is these coefficients Xc. And what we're also trying to do is we include as many possible candidate functions of pi q. And we want to get rid of all the terms that are not relevant. So we want to sparsify the differential equation. And in terms of loss, we can just sort of put everything on the left-hand side, and we have this loss function that tries to minimize for Xc. This is this Xc function, or matrix that contains all the coefficients of this right-hand side. And we want to minimize also the number of non-zero terms in Xc, so that we get a simple sparse differential equation. And this is why we add this L0 regularization term. So this is a minimizing number of non-zero X's. Now, this equation assumes that we know what pi p and pi q are, these dimensionless inputs and outputs. But in reality, we don't know what they are. And what we want to do is we want to also minimize over phi, which maps the dimensional inputs and outputs to the dimensionless inputs and outputs. Okay, so this is now this is the problem we're trying to solve. And if you remember, this maps to the hypothesis that I proposed at the beginning, which is we're minimizing both over the mapping between inputs and outputs, and we're minimizing over which set of dimensionless inputs and outputs to use. So to kind of illustrate how this method works, we're also going to use the rotating hoop problem. We have the same inputs, and now we are using time also as an input, and because we're trying to non-dimensionalize time as well. So we take time and we generate candidate timescales. And we take this equation d phi equals 0, and we also generate candidate dimensionless inputs. So that's m, r, b, g, omega. And for each one, we say, oh, this is a possible dimensionless group. And generating them is actually pretty cheap, but we have to, because there are infinitely many. So the null space of D is infinite. So we have to put bounds on the powers. For example, in this case, we say we want the maximum power and the minimum power to be 3 or minus 3. So we have this table of possible dimensionless groups that we want to find which one is the best one in our equation. And what we do is we take, let's say, in this case, we're looking for 2 dimensionless groups. We sample 2 dimensionless groups from this table, and we sample 1 time scale t. And these are possible ways of non-dimensionalizing our equation. And we transform our input-output data into a dimensionless input-output data. And let's say we have R possible combinations. So we have R dimensionless combinations. So this is R data sets. And each data set now is non-dimensionalized in a different way. So we take each one of these dimensionless data sets, and we solve this sparse identification algorithm that gives us the differential equation. In this case, the output is x double dot non-dimensionalized by t squared. And again, our right-hand side has coefficients that are dimensionless inputs. And this theta is actually, for example, x squared, x cubed, polynomial in this case, but we can also include sines and cosines. And we're trying to find Xi for each one of these dimensionless combinations. And at the end of the day, we solve that for each possible non-dimensionalization, and we take the non-dimensionalization that gives us the lowest loss. Here, it's the lowest log loss, and we just plot them in order, and we say, oh, this combination, this non-dimensionalization is the optimal combination. And now we replace this combination back into the equation, which is what we solved here. And because here we assumed the equation to have polynomial features or polynomial right-hand side, we get this equation. Here we're also assuming it to be a third order polynomial. And if you compare it to the previous equation, it's exactly the same, except now because our dimensionless coefficients on the right can only be on the right-hand side, So what we get is pi1 equals is the same as 1 over epsilon. So you look back at pi1 here, it's b squared over m squared rg, and that's just 1 over epsilon. And pi2 is gamma over epsilon. So just the whole equation divided by epsilon. And now, of course, you can take these dimensionless groups and they're interpretable, physically interpretable. One is the inertial term and the other is a pitchfork bifurcation parameter. Again, we discovered these groups. And if we assume our library to be a polynomial library of cubic order, so just powers of 3, then we get this equation. And if we assume it to be a power of 7, we get more terms because we just get an expansion of these sines and cosines. So it's just the Taylor, what we get is a Taylor expansion. And if you look at the actual solution of x as a function of t, then you can see that the test case and the polynomial, the septic polynomial exactly match. So you have, even though this is a polynomial function that represents some trigonometric functions, it does pretty well when we solve it numerically and matches the original solution. But in any case, even when the solution, when we solve this approximation that's cubic order, and the solution doesn't match the original data, we still get the dimensionless groups that we're looking for, which are pi1 and pi p, which correspond to 1 over epsilon and gamma over epsilon. And we apply the same algorithm to the Rayleigh-Bénard problem, where here we're solving, we have a hot plate at the bottom and cold plate at the top, and we have these for a low Rayleigh number, we don't have any diffusion happening, and then after a certain threshold, then you start getting these rolling convection cells. And these depend on these input parameters, which are the height h, gravity g, alpha, which is coefficient of thermal expansion, all these delta t, and kinematic viscosity and thermal diffusivity. So, and here we know that a physically meaningful output is this q, which is the integral of the gradient of the temperature in z. So, and that's the norm. So if we just take this q as the output, that's now our pi q because it's already dimensionless. The question is, can we find the Rayleigh number from these inputs using, again, this dimensionless Cindy method? And what we get is a differential equation that actually gives us this pitchfork bifurcation that's well known, that for low Rayleigh number, there's no convection. And for larger Rayleigh number, then you get these rolling cells with different q as a function of Rayleigh number. And these, for these like points in the middle, these are our training set, and we can also generalize for simulations that have larger and smaller Rayleigh number. And this is the Rayleigh number, which is nu kappa over g alpha delta t l cube. And because we found this differential equation, which has, this is the normal form that has a pitchfork bifurcation, we also find this critical Rayleigh number as a number when we discover it, which is here in this case 1878. And we find the Landau number, which is 4.6 10 to the minus 5. So conclusion, because I'm out of time, just to allow for a couple of questions. So we sort of came up with a hypothesis saying that we want to find the best dimensionless groups that map the inputs to the some inputs to outputs. And we proposed a hypothesis based on which we developed our methods. And we showed that in many cases, in these specific cases, you actually find the dimensionless groups constrained by the Buckingham pi theorem. And you find non-dimensionless groups, at least. And then we showed also in the case of a Cindy method, dimensionless Cindy method, that we can also find a differential equation along with the dimensionless groups. So for future work, we want to make these methods more robust to noise in some cases, and want to use real-world data, because all of these were sort of toy problems where we could tweak our methods in such a way that we can improve them based on the toy problems where we know the dimensionless groups. But in many cases where we don't know the dimensionless groups, developing the method will become much more interesting. And we want to improve robustness, as I mentioned, and the efficiency. Like in the case of dimensionless SIMD, this is still a very slow method. We want to make it faster. With that, thank you. And if you have any questions, and if you have time, please go ahead.
I'll ask a question. So for the real world data, have you started on that at all? Like, do you have any idea of like how well this is going to work, or is that still like in the future?
We started on a few projects that where we don't know the dimensionless groups. One of them is the stress dip problem in the granular heaps. So if you have a granular material that's granular heap, sometimes you have a stress dip in the middle at the floor. And we don't know exactly why and when this happens as a function of the input parameters. So that's like a long-standing problem in granular materials. And what we're trying to find the most significant dimensionless group that controls that effect. We're working on that now, but we don't have any results. And when we do, I'll let you know. But another one is in non-Newtonian fluids, where sometimes we assume the dimensionless groups that we have are from an analogy with Newtonian fluids, that these are the most significant ones, that they control the bifurcation in the flow. And so we have also a collaboration with some people on getting simulations and trying to see if these are actually the most significant dimensionless groups. In both of these cases, we're using simulations as data. Yeah, so there are other, I think we're sort of actively looking for real world data. That if you're aware of some where you have experimental data, that would be, of course, much more interesting.
Mm-hmm.
Yeah, my question kind of relates to that, the real world problems as well, which is, do those problems fit this assumption that we talked about early in the talk, which is that the dimensionless groups of the outputs are well known? Yeah, because I feel like many problems, maybe that's not the case, especially these unsolved problems.
Right. Yeah, that's a good point. So this is another thing that we're sort of trying to figure out, which is how to best non-dimensionalize the output along with the inputs. And so one way to the naive way to do that is you non-dimensionalize the output in different ways, as sort of a hyperparameter, and then you optimize your algorithm for each one of these, which is very expensive, and then you pick the loss that the best loss you get from these different non-dimensionalizations of the output. So yes, for example, let's say in the Duffing problem, you have to non-dimensionalize the output. It's not trivial. The non-dimensionalization of the output is not trivial. In that case, it's going to be, we can't use these algorithms. But in many cases in fluids, or in many cases that we looked at, the non-dimensionalization of the output is pretty straightforward. And it might be that we can assume some non-dimensionalization of the output, then learn the dimensionless inputs, and then iterate, and then relearn the dimensionless outputs based on these dimensionless inputs in an iterative way. So there are ideas out there to fix that problem, but yeah, that's a good point that we have to address.
Okay, thanks. Yeah, you also kind of, my second question was just sort of why you can't just also sort of optimize for the dimensionality of the outputs, but I think you answered that it's not necessarily a theoretical issue, it's more just practical, that it's kind of more expensive to do this triple optimization problem.
Yes,
So thanks.
exactly. Yeah, there are a lot of sort of efficiency problems which with each of these methods. For example, the first method is extremely efficient, but doesn't generalize well when you're looking for more than one dimensionless group. The dimensionless SIND will give you a differential equation and the dimensionless groups, but it's extremely inefficient. And there are ideas on how to make it more efficient by including, for example, instead of generating all these candidates, to include the dimensionless loss or this Buckingham pi d phi equals 0 constraint in the loss, so that you're or using a hard constraint. There's something called a constrained SIND algorithm, where now this is a constraint rather than just generating all these different combinations. So there are a lot of possibilities out there that would be happy to work on that with people who are interested in doing it.
I also had a question about, also I want to be mindful of the time. It's 1:05. So yeah, I mean, I had a question regarding, so it seems, I mean, I don't know, like I don't, work in the fluid world, although I do sometimes talk to collaborators who do. But often what happens is that, yeah, differential equations themselves are not available. And it seems that out of the three that you described, the best performance was, you can identify groups. So the second method was okay. But once you start adding these SIND terms, things become even better. But I think just to add a complementary dimension to some of the suggestions that Karen and Alex made, I'm wondering, have you thought about multi-scale problems, especially where there's some kind of regime shift, or I mean the behavior is not very continuous, right? Maybe
Right.
I'm just wondering if you've thought about this, or if you have any work in progress.
Yes, I definitely. So my kind of previous interest was before starting working on these methods was granular materials. So these in these cases you have a lot of multi-scale effects, and it's not clear what's happening at the different scales. You have different spatial and temporal scales, and we're definitely thinking in this direction, and that's sort of my interest in multi-scale systems. It's harder to think of problems where we don't know the dimensionless groups. So what we're trying to find is problems where people didn't really think about what's the best dimensionless group, because every field has some kind of theory in terms of what are the dimensionless groups that are the most significant. But we're definitely looking, for example, in granular materials, you have force chains and you have length scales that happen at the mesoscale that we're not sure if they're important or not, like non-local effects, and getting dimensionless groups that kind of capture these effects from the data, from this, that could be just from simulation data, is very valuable. And this is sort of the direction of interest that we're going into. This is kind of the purpose of these methods at the end of the day.
Yeah, I mean, and I should also say that some of this work seemed really interesting to me, and is still very interesting to me, because I mean a common discussion that we have is just a very simple one, right? How do you non-dimensionalize things in machine learning, right? There's heuristic things. Okay, you can do the standardization and so on, but I think it would be great if, and again, this is not necessarily free. I think this can be also done collaboratively. But if there was just a more modern way of handling things, and again, this requires some form of domain expertise, okay, depending on the problem, you do this or not, but in a more model agnostic way, if there was a way to say oh, here's how you should do, non-dimensionalization, and a better way. And maybe it's the second method that you suggested, right? Like you make some guesses, and that's why I was interested in the statistics. Like maybe it works like 50% of the time, in which case it's still better than like, you know, doing the dumbest thing. If it works 20%, maybe okay, maybe not worth the investment.
Yeah. So if you have a problem in mind, because it's like we also noticed that depending on the problem or the data that's available, you have different ways of non-dimensionalizing, like different, for example, the output might have a non-trivial non-dimensionalization or not. So if you're thinking of something that would be like, I would be really interested in seeing like what's the type of problem you're thinking about, and when, of course, we can collaborate on that to see if, like, you know, we can get the desired non-dimensionalization, and then based on the result we improve the methods, etc.
I was really interested in this too, because I've had this problem that it's like very different scales, so it's really hard to deal with like how you choose the initial normalization for like using machine learning with it. Anyway, Dirk, did you have a question? Or sorry, it looks like you were raising your hand, but
can you hear me?
Yes.
Oh, well, first place, thank you to the host. I'm watching here in the Netherlands, far away from where you are. I work on signals from the MRI scanner, and these are complex values. So what do you do when it's complex values?
That's interesting. I think what are the dimensions of these complex values?
It are sinusoids, all sinusoids with different dampings.
I see.
And so that's not too difficult. But these sinusoids are complex values. The signals are complex values. And I hate to change the code from complex values to real values. It's a lot of work. At present, the code that I use, it's not your field, is all complex values stuff. Of course, you understand I use Fortran 2018, by the way.
So your complex, these are complex outputs, I'm assuming. These are your quantities of interest are complex values, which are...
Yeah, and the parameters are physical, so they are real values.
Right. I mean, I imagine that it would be possible because these outputs are, in a way, are they dimensionless or do they have dimensions?
The parameters are, for instance, frequency or damping, that's the same. And it doesn't go, or moles, how many molecules you have in the brain, for instance. Also real value. It's just that the signal is complex value.
I feel like
and the equations are complex value.
I see, yes, right. I mean, it should be possible to work in complex space. That's a really interesting point that like I never even thought about working with complex numbers, but that would be...
You can find it on the internet. There are people working on it, but it's beyond just a simple applied physicist. That's beyond me what they still have to do.
So in the case of like complex outputs, I imagine that you can, to apply a data-driven method, you can just use like a two-dimensional, let's say you just have one-dimensional complex output, you can use a two-dimensional real valued output to represent that complex number and then try to do the fitting based on that. And I don't know if that would solve the problem or if it's actually, if it makes any sense, but that's the first solution I can think of.
Yeah, well, at the moment, I cannot do it, but I'm going to try.
Okay, yeah, I'll be happy to, you know, help if I can.
Okay. I think I'll send you an email so that you know who you have been talking to.
Yes, that would be great. Thanks.